Hello and welcome to another tutorial on ZIVA VFX. In this video we're going to be looking at materials, so the properties of materials, how to layer them, and thus how to get varying material properties across the same surface. So in this scene I have a tissue mesh. It's not a watertight volume, it's just a surface, which is fine from ZIVA's perspective. If it's a non-watertight volume, ZIVA is just going to tetrahedralize the surface if you turn it into a tissue. And you notice that the tet mesh is denser in the areas that aren't these kind of raised plates. And the way I achieved that was just painting the tet weight, which I showed in the video on the tet mesh. So you can go back and look at that as well. But just to recap, the idea with that is you right click on the mesh, come down to paint, ZTet weights, and then the area that you paint will multiply against the surface refinement attribute on the tet nodes. If I turn that to 1, you'll get a slight resolution change, 0, nothing, and 2 is going to subdivide it twice if you like. Right, so if I play this back now, you're just going to see the tissue is just going to fold, even though we have higher degrees of freedom in the areas that aren't the plates. What you're going to see is the tissue is going to be pretty uniform as it folds down. So play that back now. So while it is kind of, you do get some cool effects as it stretches and it folds. It's kind of not super exciting. So what would be nice is if we could have a varying stiffness across the material where the plates sort of preserve their shape, and the area between the plates kind of deformed a little bit more, and all the stretching and deformation happened at that level. So if I come across to the Z material node now, click on that, you'll notice we have some attributes here, and the attributes that I'm going to be looking at in this part of the video are the Young's modulus attributes. And remember, these two attributes multiply together to give the final value, similar to stiffness in attachments or strength in Z fibers. And so currently the Young's modulus by the way is the engineering term that basically means stiffness. So instead of just calling this stiffness, we retained the term Young's modulus because we're working with a real world physical solver. The Young's modulus is actually a value that you can look up for different materials. So if you wanted to go into Wikipedia or something, look up the Young's modulus for jelly, or the Young's modulus for bone, or wood, or whatever. You should be able to find those values and plug them into ZIVA, and assuming the solver scale and everything's right, you should get the behavior of those materials. So that's why we left it as Young's modulus rather than stiffness. So right now the whole surface has the same Young's modulus as muscle. So 12 times 10 to the 3 is our default value, and it's roughly what the Young's modulus would be for muscle. And right now that value is uniformly spread across the surface. So in order to have a varying stiffness across the surface, what we want to do is add a material layer. So under the ZIVA menu, with the tissue object selected, under the ZIVA menu I'll come down to add tissue property, and I'll select material layer. And you'll notice that ZIVA inserts a material above the current material. If I added a third one, it would put another one on top of Z material 2. But we'll just work with 2 for now. And what I'm going to do is make the material on top, I'm going to make it 100 times stiffer. So I'll make it 12 times 10 to the 5. And if I play this back now, you're going to see that the whole material is much more rigid. And it's still uniformly rigid. So in order to get the variation of materiality across the surface, what we want to do is paint a map. So if I select this, and I right click on the mesh, I'll come down to paint, and I'm going to paint the map of the material on top. So in ZIVA, the material on top in the channel box is the material that takes precedence. So the materials aren't additive, they don't multiply together, it is the material on top that takes precedence. So the map that you end up painting is sort of akin to the alpha map in Photoshop, for instance, in layers. So in the areas where you paint black, that indicates to ZIVA to take the material properties of the layer underneath. and we don't allow you to paint materials on the base layer. So Z material 1, I couldn't paint black here because we need to ensure that there's materiality on the tetrahedra at all times. So with the 2 materials set up, wherever I'm going to paint black on material 2, it's going to take the properties of material 1. Cool, so I'll do that now, just quickly. And if you turn the solver off, you'll actually be able to paint a bit faster because it's not going to try and update with every stroke. It's a fun tip. Cool, so now I'll switch the solver back on. So now when I play this back, hopefully you're going to see the plates preserve their shape a little bit more, and the area between the plates is going to deform. Cool, so I can just scrub the timeline now. And you're going to see that happening there. So this is a really powerful way for getting varying materiality across a surface. And it will also work if you have a watertight volume as well. So what ZIVA will do in that instance is it will just propagate the values on the surface to the interior tets. In the next video we're going to talk about volume conservation. As always, thanks very much for watching.